Okay, so they didn't really label things on this diagram, but here we have theta. Remember, this is our arc length here, so maybe label that as S. And then our radius is from here to here, right? It's R over here. Okay, so there's a lot of applications that might just focus in on it and ask you, what is the length of the circular arc, which is S. Okay, so in that case, sometimes we simplify the definition of radians. And let me show you what I mean by that. So definition of radians is S over R. Okay, but what if I were to multiply both sides by R? So if I multiply both sides by R will be gone here, and then I'm going to have R theta on the other side. So by doing that algebra step, it's solved for S now, right? You guys seeing it? Maybe I'll put in the pencil here so that you see it. If I multiply this by R, gone. Multiply this by R, what am I left with? S equals R theta, okay? So it's just kind of a shortcut formula for dealing with problems that ask for the arc length. Technically, you don't really need it. We could always use this, but then you just got to solve for S. So it doesn't matter. They're one and the same. Here's what you got to remember whenever you use this, and here's the catch that a lot of students forget, at least early on. Theta must be in radians. I cannot punch in degrees into this because this is derived from the definition of radians. So theta must be in radians when using this formula. Okay? It's a big must, a big requirement. Okay, so let's take a look at 19. Find the length of the arc on a circle of radius 15 centimeters intercepted by a central angle of 60 degrees. So here, I'll give you another visual aid of this, what's going on. So we've got an angle in the middle. They're giving us the radius. So from here to here, it's 15. I put that at a bad spot because we got to put the angle in there. I'll put 15 centimeters here, from here to here. The central angle from here to here is 60 degrees. Okay. The question says, find the length of the arc. So it's this curved distance that they're asking for. Well, I have 2 out of the 3 of this formula, except I can't throw 60 degrees in this formula. I have to remember to make sure I put it in radians. So the first step, step 1, put theta in radians. Some problems, maybe they already give you the angle in radians. Perfect. It's ready for the formula. In this case, they didn't. So put theta in radians. So I've got 60 degrees, and I got to multiply that by pi over 180 degrees. Okay, degrees cancel out. So I have 60 pi over 180, but that's a 1/3 relationship. So it's pi over 3 radians, or 1/3 pi. Okay, so now step 2, just use the formula. Use formula to finish it off. S equals R theta, as long as theta is in radians, which we took care of. So S equals 15 centimeters times the angle of pi over 3. And then sometimes they might ask you to round it to the nearest decimal. They may say keep it in terms of pi, which if that's the case, it'd be 5 pi. But here I've got the decimal answer. Just punch that in, and we get 15.71 centimeters. Okay. All right, pause and try 20, and then we'll take a look at these clock problems below to wrap it up. Okay, so 9 radians times the 3, S equals R theta. That's it. You might be wondering which to use, but remember, your answer is not an angle. It's a distance, so that's why we'd use feet here, okay? 27 feet is the answer. Okay, let me take you through 21, and then if you guys try 22, and we'll be done for the day. The minute hand of a clock is 8 inches long and moves from 12 to 2. how far does the tip of the minute hand move? Let's go ahead and draw a picture of this situation. All right, so we've got the minute hand of a clock. It says it's starting at pointing at 12, and then it rotates across to the 2. So the first thing and first challenge with this problem is we got to figure out how many degrees that is. So step 1, how many degrees did it rotate? Okay. Well, I mean, sometimes if you got to look at a clock to remind yourself how many minutes that is, right? That's 10 minutes. It's 10 minutes out of the 60, right? So that's 10 minutes out of the 60 minutes for an hour. So that is 1/6 of an hour, right? It's 1/6 of a rotation. Because obviously when it rotates all the way around 360, that's 60 minutes. So what you need to figure out is what is 1/6 of 360 degrees? And it works out to be 60 degrees. Okay, so whatever the time is, figure out what fraction of the hour that is, and then just multiply by 360. If it's 15 minutes, we do a quarter of 360 and say 90 degrees. Okay, so that's the first step. Figure out the degrees, and now it's going to be a lot like number 19. How do I figure out how far? It said how far that tip moved, right? So hopefully you understand that's S. That's what we're looking for. S equals what? Okay, so then step 2, we got to convert this to radians now. So put theta in radians. So I've got 60 degrees. We just did this up here. Don't really need to redo the math. 60 degrees is equal to pi over 3 radians. All right, and then the third step, use the formula. So S equals R. They said it was 8 inches long. So 8 inches times theta, which is pi over 3. Okay, so if they say to keep it in terms of pi, I'd multiply straight across and say it's 8 pi over 3. If they say to throw it in your calculator, around to the nearest tenth maybe, or something like that, we punch it in to get 8.4 inches. Okay, you try that. 22, pause and give it a shot. Okay, so here's 22. 3/4 of a rotation, because 45 out of 60 is 3/4 of the hour. Okay, or you can add up the 3 right angles that you're using. 270 degrees, which equals 3 pi over 2 radians. And now you can multiply that times 2. 9.42 inches is the length. Okay. All right, the only last thing I want to show you is just how to set up one of your OTI problems on the next page. Take a look at 19. I'll help you set up the sketch and then let you be done. All right, so 19 and 20 are just like that set of problems we just did, where we're going to use S equals R theta. Okay, they're just giving us what's the distance 52 degrees north of the equator. So let's just say we're looking at the Earth from outer space, from kind of the side, and let's just draw the equator right here. Okay, they just gave us the radius of the Earth right here, 3959 miles. That's R. So if R is 3959, and this says 52 degrees north of the equator, they're giving me this angle. I'm not going to draw that in there. Just going to put 52 in there. Okay, and obviously our Earth and this arc length is the distance. Our distance on Earth is always kind of an arc length. So they're asking for this right here. Okay, so it's just like the problem we just did. Your job is to figure out 52 degrees in radians, and then you can figure out the arc length. Okay.